podcast is brought to you by LMU Munich.
I would like to thank Dieter and the other organizers for this wonderful conference and also for giving me the opportunity to give a talk here. It's been a great conference. I'm going to talk about, I've been asked to review aspects of topological strings. It is a vast subject, and I will try. Since their introduction about more than 2 decades ago, they have had many different kinds of applications and extensions, and it involves basically a simpler kind of a setup where various aspects of string theory play out, and they interact with the full string theory at the same time. So it's kind of, even though it's a kind of like a baby version, it's in some sense a subsector of the full string theory, and it has interesting implications about string theory itself. And it leads to understanding aspects of string theory in a more deep sense, in a deeper sense. And there are many applications to things like supersymmetric gauge theories, or things having to do, for example, with the counts of the microscopic states of black holes, or strong coupling dynamics, and so forth. So it's interesting for many reasons. On the other hand, it is a very diverse subject in its own right. Therefore, it's going to be very easy to get lost. And so one thing to keep in mind to kind of get a map of where it's going is that there are various Z2 type operations which map one part to the other. And there are all these, you can go from one corner to the other by going from one side to the other. These operations involve this type of thing. The A version versus B version, related by mirror symmetry. Open strings versus closed strings, which get related by larger dualities. Non-compact versus compact, which in the target sense gets related to gauge theory versus gravity questions. Non-compact versus compact, I mean in terms of target space. Refined versus unrefined turn out to be related again to aspects of gauge theory versus gravity questions. Wordsheet versus target perspective. Internal geometry of string like Calabi-Yau versus the total space, so topological versus the physical space. Perturbative versus non-perturbative. So there are all these Z2 type questions you can ask in almost all of these corners. You can go and basically ask, so it's 2 to the power of whatever you can count here, kind of corners that you can go to. So it's a bit complicated. So I'm going to kind of try to give you almost all these corners, but of course I can't succeed. So I'll just try to give you a flavor about all these various corners and how they fit together. And basically this work is related to the work of many people over many years. So I'm basically summarizing the references that I'm using here. So this is the extended version of the references, but I will just refer to them in the abbreviated form so that it doesn't distract from the presentation itself. So this is the outline of my talk. I'll first review the definition of topological strings. So I will describe aspects having to do with the wordsheet definition versus the target definition of topological strings, closed versus open, A versus B, and regular versus refined. I will then say how we actually go about computing the topological string amplitudes, in particular the role of the holomorphic anomaly in that context, also the role of Largent dualities, and in particular relation between Chern-Simons and how that leads to topological vertex formalism, also the matrix model, and also how that leads to topological recursion formulation. I would also talk about then application aspects of topological string in the context of superstring itself, in particular the relation to counting of the BPS states of a black hole. I talk about how these aspects of topological strings can be used to count 5-dimensional spinning black holes, charged spinning black holes, as well as charged BPS black holes in 4-dimension. I then switch gears to gauge theory application, where I talk about applications to gauge theories in 4-dimension with n equal to 2 and n equal to 1 supersymmetry. I talk about wall crossing phenomena in 4D as well as its relation to 3 dimensions and n equal to 2 dualities. And then I'll end with some open questions. So Type 2A string theory has space-time dimension 10. In many applications, we want to consider 4-dimensional situations, and a very natural choice ends up being a 6-dimensional Calabi-Yau threefold, which preserves in 4-dimensional setup an equal to supersymmetry. So this we're all familiar with for a long time now. And for many questions related to the long distance or low energy physics, questions that we want to answer end up being related to considering minimal kind of maps between the map from the Riemann surface to this geometry, the minimal area. In fact, more precisely, holomorphic maps, which automatically will be minimal area. So we end up studying a subsector of all the string maps, which are kind of minimal or supersymmetric in a sense. So objects which preserve some amount of supersymmetry localize the maps from the worksheet to the target to be on the holomorphic subsector. So since Minkowski space has no compact cycle, this in particular means that these kind of maps from the worksheet are holomorphic and sit perhaps non-trivially inside the Calabi-Yau threefold, but they should map to a point as far as the 4-dimensional aspects look like. So it's kind of like an instanton from the viewpoint of 4 dimensions. So therefore, the problem of map from the Riemann surface to the full space reduces to holomorphic maps from the Riemann surface to the internal space. So basically, we factor out from the full superstring problem a mini problem, which is the map from Riemann surface to the Calabi-Yau threefold. So the A model topological string is concerned basically with counting such maps, counting these instantons. And the reason counting comes in is because if you just formally count what is the dimension, this is the space of this map, it's 0-dimensional, so you might just have to add which discrete instantons you have and just add them up. More precisely, it ends up that even though the formal dimension is 0, sometimes you get some family of such holomorphic maps, and you have to do some suitable integral which is dictated by aspects of topological strings, and you basically end up getting some analog of counts which end up being not necessarily integers. So in principle, you get some e to the minus the area, which is basically you take this x, which is mapping the Riemann surface to the Calabi-Yau, you pull back the Keller form on the Calabi-Yau, which basically gives you the area of the Riemann surface. And you evaluate these integrals or this moduli space of these maps, and these are rational numbers, and that's what topological A model string is supposed to be doing. More specifically, for a fixed genus, we fix the genus of the Riemann surface, and we sum over all maps, which now depends on the Kähler parameter of the Calabi-Yau because of the area here. So you get some object which depends on the Kähler parameters of the Calabi-Yau, and these are known as the Gromov-Witten invariants, these rational numbers which depend on the class of the map for every given genus, for a class of the map from the Riemann surface to the class gamma, which is in the second homology of the Calabi-Yau. And then we sum up all these amplitudes, the free energies of genus G, weighing with the string coupling constant as usual, and exponentiate to get the partition function of the topological string. So the topological string partition function is a function of Kähler parameters, as many as the Calabi has those, and one string coupling. Naturally, we can add D-branes into the story. Basically, as usual, we have some kind of a nice subspaces in this manifold that we turn on, which we put the D-branes on. It turns out that for the purpose of preserving the symmetries of topological string, all you need is Lagrangian submanifolds. In applications in superstring, these Lagrangians get promoted to special Lagrangians. So you have these Lagrangian subspaces of this manifold, and you get maps from the Riemann surface with the usual property that the boundaries map to the Lagrangian subspaces. They could intersect and have nice, interesting properties. In the full superstring, these Lagrangians, if you go back to the original question, these could have different kinds of branes, depending on what kind of what does the rest of the brane look like in the space-time. If in the rest of the 4-dimensional space-time, they fill the whole space, that would correspond to D6 branes. And if they fill a 2-dimensional subspace, they correspond to codimension 2 in the full space. And both of these will be interesting. So we'll have both viewpoints. They will both get related to questions of topological string of the same type, though they will have different physical applications, clearly, depending on which one of these two cases we have in mind. And as usual, we put the multiplicities, so you can put the n of them, not just one, so you have interesting dynamics living on them, the UN dynamics that we are familiar with in the context of D-branes. So if we consider the Lagrangian submanifold with n D-branes on it, you could ask, from the perspective of topological string, what kind of dynamics lives on it. And it turns out the dynamics ends up being a UN Chern-Simon gauge theory living on this Lagrangian submanifold. In particular, if you look at the expansion of the topological string with these boundaries, then you have, as usual, n to the number of the boundaries that you get on the Riemann surface, lambda to the power of 2g minus 2 minus the number of holes, and this number here, which ends up being expansion of the Chern-Simons on the corresponding Lagrangian submanifold, perturbatively expanded in terms of n and lambda. In this context, the open string field theory, Witten's open string field theory ends up being, which is abstractly Chern-Simon theory, ends up being the usual Chern-Simon theory. So this is basically what one gets, and there could be on top of these Chern-Simons, there could be instanton effects, and there typically are, which end up giving you additional loop observables, Wilson loop observables of the Chern-Simon. So this is only the leading three-level computation that you would get, but then there could be instanton corrections. So one can also obtain knot invariants more specifically, engineer them in the following way. If you take the Lagrangian and view the geometry of the manifold, the Calabi-Yau that it sits in, only in the neighborhood of it to look like a cotangent of this Lagrangian, you could consider adding an extra Lagrangian to the story, which intersects the Lagrangian original one along the knot, and extending in two other directions normal to the knot to make a three-dimensional space. And if you compute what kind of dynamics you get, is basically you get extra states, open string states which are stretched between these two L and L prime. So you get two different Chern-Simons living on each one of these two Lagrangian submanifolds, and then you get bifundamental matter which lives only on the knot. You can integrate that bifundamental out, and you get observables of this type, where the U and U prime refer to the Wilson loops of the gauge connections living on L and L prime, and you get the sum over various representations, allowed representations basically. So this is kind of a wordsheet perspective of the topological string, and one could ask, what about the M-theory interpretation or definition of it? Can we give a different perspective about what it is? And it turns out it's possible. So in M-theory, as we know, the type 2A gets lifted up to 11-dimensional space. So the space-time, which used to be 4-dimensional, grows an extra circle. So we have R4 times S1 in addition to the Calabi-Yau that we have talked about. Now, let's do the following. We replace the R4 by tab naught. So topologically, we don't do anything, but geometrically, we do something. Namely, we have a tab naught geometry now with an extra circle, which doesn't grow at infinity. And we don't touch the circle for now. And then we do the following. We change the geometry a little bit. Namely, we replace the tab naught times the circle by a twisted tab naught times the circle with a twisting parameter q. And what that means is that if you view tab naught in a complex coordinate, that's two complex coordinates, z1 and z2, the theta and the coordinate of the circle by theta, as you go around circle, if you shift the theta by 2 pi, you rotate z1 and z2 in opposite direction given by q. This operation is of course supersymmetric if q is a phase, and so it's not a bad thing to do in this space. And so basically we are replacing this tab knot times the circle with a twisted tab knot times the circle. Let me call it Y. So it's a 5-dimensional space. So the statement is the topological string on the 6-dimensional Calabi-Yau is equal to the M-theory partition function itself on this geometry. So if you want to know the definition in M-theory of what topological string is you take the 6-dimensional Calabi-Yau times this 5-dimensional twisted tab knot of the circle, where you identify this twisting parameter with e to the topological string coupling constant, e to the lambda, and this would be a definition of the topological string. You can also ask what's the interpretation of the putting this Lagrangian D-branes, or what I call A-branes, and how does it fit in M-theory? Well, that will depend on whether we are filling the space-time with D4 or D6 branes. In the D6 branes, they will become Kaluza-Klein monopoles, and the Calabi-Yau gets changed to a G2 holonomy manifold. In the case of D4 branes, it becomes M5 branes. So let me actually concentrate on the latter case, which turns out to be interesting. For various things I want to say later today. So you take, again, you start with the 6-dimensional Calabi-Yau that we talked about times this 5-dimensional extra space, which is this twisted tab knot. And you basically add the Lagrangian to the story, namely you choose a Lagrangian inside the Calabi-Yau, and you choose the rest of the space. You need 3 more dimensions, and the circle is circle, you don't do anything. And you choose one of the 2 directions in the tab knot as to be the space that the M5 brane fills, and therefore it inherits the twisting of the corresponding tab knot. Namely, as you go around the circle, this C, this complex plane, gets rotated by Q. So this piece, so the M5 brane basically lives on L3 times this twisted cigar, or something that we call Melvin cigar, which you have a cigar geometry with a circle, with this property that as you go around the circle, the cigar rotates. So the statement is then that the partition function of M5 brane in this geometry, in the Calabi-Yau, is equal to the topological string, open topological string with this Lagrangian L, which in turn is the Chern-Simon up to corrections involving instantons on L. So again, this gives you a physical definition of the topological string in terms of superstring or M-theory amplitudes directly. So this is in some sense the precise statement that these are subsectors of M-theory or superstring theory. We can move on to one further layer of subtlety, which is called refined topological string. And this we cannot do this in the general case of Calabi-Yau, which is compact Calabi-Yau. We can only do it if Calabi-Yau is non-compact. If the Calabi-Yau is non-compact, in particular with an extra U1 symmetry, which turns out to be part of an R symmetry of an n equal to 2 in 4 dimensions when we compactify the type 2 strings on it, we can do a refinement of topological string in the following way. So instead of this twisted tab knot, which I call this Y, where we had this definition was that as you go around the circle, we rotate the 2 of the planes of the tab knot in opposite directions by Q and Q inverse. Now we can do a further refinement by twisting the 2 different planes in 2 different directions, 2 different amounts as we go around the circle. So as you go, theta goes to theta plus 2 pi, you rotate Z1 by Q1Z, Z1 and Z2 by Q2Z2. So we have basically this extra degree of freedom added to the story. However, this latter operation is not such a great one as it looks because it's not supersymmetric. You're breaking supersymmetry by doing arbitrary rotations independent of each other, unless we compensate this non-preserving of supersymmetry with some other action in the internal geometry of the Calabi-Yau. So that's why we can only try to do this in a supersymmetric way only when we have a non-compact Calabi-Yau, where we can use part of an R symmetry, a U1 rotation of this non-compact Calabi-Yau to improve this non-supersymmetric kind of operation. So what we do is we take this non-compact Calabi-Yau, and in the U1 direction, you rotate this by Q1, Q2, and Q1, Q2 inverse, actually, I should say here, so that the product of them will preserve supersymmetry. So in such a way, you'll be able to have the twisted tab knot, which is now depending on two parameters, compensated by this. So as you go around the circle, you not only rotate the tab knots in these two directions, but also the internal Calabi-Yau to compensate for what would have been the breaking of supersymmetry otherwise. And in this context, you can define this M-theory partition function of K to be the definition of refined topological strings. In fact, we don't have a better definition in this sense. That is, we still don't have a nice worksheet definition, as I started my talk with. So in the context of the undefined topological string, I gave you the worksheet definition. Analogous to this, we don't have it. So in other words, the connection with superstring allows us to define the refined topological string via the M-theory amplitudes. Similarly, this can be extended to the open string definition of you can refine also the open string similarly just by embedding the same way I told you about, putting the Lagrangian here. You get that embedded, and in that context, the analog of the refined topological string ends up being related to aspects of Khovanov invariance. So it's some kind of a refinement of Chern-Simon theory. So this so far was the A model. Now I apply a Z2 and all I have talked about, and now I repeat. No, I will repeat some aspects of what I have said in the context of the B model. B model is basically the statement that if you take type 2A on a Calabi-Yau M, it's equal to another type 2B on its mirror, that we know, on a mirror Calabi-Yau. So in this context, we say the A model topological string on M is the same as B model on W. So that's, if you wish, a definition of B model. You can also give a direct definition, but anyhow, this serves as a purpose, for a purpose fine, as a definition of B model. Now, B model turns out to be much easier to compute in many cases. And in particular, the genus zero amplitudes for B model, thanks to mirror symmetry operation that was hard on A becomes easy, gets related simply to computing periods of the holomorphic 3 form, as is familiar, and the partition function of genus 0 becomes the prepotential of these periods, which meaning the gradient of it gives you the B periods, and in terms of the A period variables. So this is all familiar, so I won't dwell too much on it. The higher genus amplitudes of the B model, instead of being these holomorphic maps that we have, gets related to a quantization of complex structure. So it corresponds to a kind of a, in the language of what's happening on the Calabi-Yau, it turns out you're quantizing the complex structure of Calabi-Yau, which is known as the Kodaira-Spencer theory. And in general, there are no direct target space definition of it, a la M theory, as I was explaining to you. So there's this extra circle that you can do. Of course, you can use via mirror symmetry the definition. In other words, you can go to the A model and define it that way. But a direct definition a la an extra circle, and an extra circle is roughly missing to make this connection with the tab not direct. However, in one case, in local case, in non-compact cases, where the Calabi-Yau is simple of this form, which is given by a curve, you can give a target space definition of it. By a various chain of dualities, you can map this. So if you ask what is the B model on a Calabi-Yau, which is like a hypersurface in this form, in 4 variables, you look at this hypersurface in 4 variables, the local Calabi-Yau, a chain of dualities will map it to the following. It maps it to a D4 brane and D6 brane intersecting on a curve with the fermion living on it and a B field turned on, making the fermion see the Riemann surface as non-commuting, with the commutation of the corresponding variables being the string coupling constant. So you have certain B field turned on, and on the intersection of these D4 and D6 brane lives the fermion. So now it's a space-time fermion living on the intersection. There's a B field which makes this fermion live on this boundary of this non-commuting space. And B-branes, we can also ask what are the B-branes in this context. The analog of the Lagrangian branes get replaced by holomorphic cycles, in which got dimensions 0, 2, 4, and 6. The usual Chern-Simon as describing what is the target space of topological string gets related to holomorphic Chern-Simon theories, and in some cases equivalence of it with matrix models. For example, in the zero-dimensional case or in some reductions of Chern-Simon symmetries, you get things having to do with relations with matrix models. And then you can ask about the refinement. At the level of the matrix model, it turns out that the description of the open string sector becomes a refinement of the matrix model, where the Vandermonde, the measure of the Vandermonde gets raised to a different power, so that changing the power of the Vandermonde is the refinement. It's called the beta ensemble. And a similar refinement can be done for the Chern-Simon for the A model. So this is so far as what the definitions are. How do we compute? One trick is the following. Topological string partition function morally depends on on one set of complex parameters and not their anti-holomorphic partners. This by itself might sound a little bit kind of tautological, because by definition I only had one set of parameters. But what makes it non-trivial is that this complex parameter space is in some sense compact. So if you have a function of some compact moduli and it's holomorphic, you can compute it. Typically it's like 1 unless there are singularities. And if you have singularities, if you know the structure of singularities, you can write the answer. So that's the idea. The idea is basically the function is 1 if it weren't for singularities. And if it's singularities on these compact spaces, study singularities and get the answer. Well, a few subtleties come in the way, but that's the general idea. One subtlety is that it's not quite holomorphic. There's a holomorphic anomaly which tells you that the amplitude want to be holomorphic, but they are not. So but that you can take care of it by studying what kind of anomaly they satisfy. And so if you look at the partition function, which formally you might have thought is holomorphic by the kind of definition we gave originally, ends up depending on the complex anti-holomorphic part of the variables. And the relation is something like del bar of z is d squared of z, some kind of a heat kernel kind of heat equation kind of system you get. I'm simplifying writing the equation, but it's roughly looking like this. And so, as I just said, to compute the amplitudes, therefore, we just need a finite set of data of understanding what happens at the singularities. This idea has been pushed I would say by some heroic efforts, to very high genus, computing, for example, up to genus 51 for the quintic threefold. So you can do very non-trivial computations now using this kind of simple holomorphy idea and studying what happens at singularities of the Calabi-Yau. And you can similarly do this kind of trick also in the context of the refined version as well. Also, efficient techniques have been developed to integrate the holomorphic anomaly equation, which looks like also itself a bit complicated. There are some techniques that one can use to simplify the task of integrating the anomaly. Now, the open A model how do we solve for the open A model? Well, I said it's given by Chern-Simon theory. How do we solve Chern-Simon theory? Well, we already know how to solve that. That's using the WZW models. So therefore, the answer of topological string A model is already done by 2D conformal field theories from long ago, so we already know how to solve that. And so there's a similar context in the B model, where the similar objects, which was Chern-Simon, gets replaced by the matrix model analog. In that context, how do we solve it? Well, there are matrix model techniques of solving them. So that's also relatively simple to do. And in the case of the open A model, if instead of non-compact geometries we have compact case, where the Lagrangian is inside the compact Calabi-Yau, then we can use mirror symmetry and reduce to questions for the B model language. So there's some techniques basically which are mimic the closed string case with some additional ingredients that come to our rescue. So now I want to shift gears. Again, now going back to the internal geometry perspective. So I was giving you a connection with the worksheet and the physical space, but now I'm going back again to the internal space. It turns out that these theories enjoy very nice features of Largent dualities. So the simplest one is the following. You take a model on cotangent of S3. This is the familiar conifold, what we call, I guess, deformed conifold. And we put n Lagrangian A-branes on the apex of this conifold, wrapping the S3. And the large n transition says basically that at large n, these branes disappear, and replacing the change in the geometry on the way, making S3 shrink and making the S2 grow, and the size of the S2 turned out to be the 2th parameter of this large n theory. So how do we know this is true? Well, the left-hand side, as I told you, is computable. The right-hand side turns out to be also an easy example of topological string to compute. You compute it to all order in n and lambda, and you check, and it works. Okay, so this is in some sense a perturbative, at least, check of the duality to all orders. One can also find the worksheet explanation of this large n duality. This is something we haven't been able to quite do in the context of ADS-CFT, for instance. But in this simpler version of the large n duality, there's a simple idea which actually leads to a derivation of this duality. And the idea is to actually go to the point to try to reformulate what does it mean to talk about the closed string side, the gravity side, at the 0 at 2 coupling constant parameter. At that point, the conformal theory goes bad a little bit. Instead, what you do, you take the gauge linear sigma description of the theory, and you describe the behavior of the theory near there in terms of the phases of the gauge linear sigma model, which involves Higgs and Coulomb branches. And then you take the RG flow, and it turns out that from the closed string worksheets, you end up getting open strings because the phases of the linear sigma model, which were in the Coulomb phase, become massive in the infrared and decouple from the rest of it, providing these boundaries, D-branes, boundary conditions, on the rest of it, so giving you D-branes. So this kind of a picture where the large n duality could in principle be derivable from a worksheet perspective if we have a formulation of what happens to the closed string itself at the 0 at 2 coupling parameter from a viewpoint which is going beyond conformal theory. Namely, instead of talking about infrared fixed point itself, as going beyond it by starting from the gauge linear sigma model, which have more information, and that somehow reproduces this picture. You can also use not observables of this Chern-Simons theory to get more information, and you can try to interpret it, what happens to this on the, so you start with cotangent of S3, you introduce these not observables I talked about, and you take it through the large n duality, and it ends up getting certain computations of these Lagrangian branes in the closed string side. And in some sense, if you take the description of the closed string side, which is this O minus 1 plus O minus 1 over P1, the resolved conifold, and you think about where you're putting these knots and so forth, you can choose various representations corresponding to what Wilson loop observables you're putting, and it ends up factorizing the pieces into trivalent vertices where you put the representation at these edges. And so the computation of the topological string ends up being related to pieces involving cubic vertices. And you can actually recover the topological string answers directly by basically gluing from the open string pieces. This is known as topological vertex. So for example, if you take toric Calabi-Yau, here I'm drawing for you the P1 times P1 example, you can cut open all these, you can cut open the internal lines, and you see these trivalent vertices, and you stick in these topological vertices, and this gives the computation of the topological string amplitudes to all genus answers simply from the answer from this trivalent one. So there's a cubic kind of field theory which are these vertices, and the internal lines are labeled by representations, and the propagators are given by exponential minus the number of boxes of these Young tableaus times the Kähler parameter, which is the size of the corresponding length. So it's a relatively simple field theory, and this solves all genus amplitudes for toric Calabi-Yau threefolds in a non-compact case. So this is a complete answer for these cases. And there's a refined version of this as well. Namely, you can do this refinement. So if you take any of these non-compact Calabi-Yaus, with all these things, with P1s or all these complicated stuff, you can actually do this refinement and compute to all genus. So this in some sense means the non-compact A model to all orders is solved, basically using this formalism, at least as far as the computation goes. The B model version is matrix models. As we said, there's the B model version of these large N duality turned out to be the duality we are familiar with in the context of the large N duality of matrix models. And it's, for example, maps the B model geometries which may look like this, which are these hypersurface type geometries I was talking about before, to matrix integrals like this. So there's some kind of a map between them, but basically the same kind of ideas tell you how you can compute, relate the A to the B. So if you want to compute the B model in this closed string geometry of this Calabi-Yau, it suffices to study these matrix models and gives you the answer to all orders. In fact, we can push this further by using techniques which was discovered in the context of matrix models to compute all these order 1 over n corrections. And in fact, you can use this principle to generalize it to all B models, and this is called the topological recursions. And what these mean really is that these topological recursions are interpreted as ward identities of the 2D reduction of the Kodaira-Spencer theory. So we just talked about the Calabi-Yau threefold itself. It corresponds to the description of quantizing complex structures. The baby version of this for the hypersurface inside the Calabi-Yau, which is a curve, is basically complex structures of the curve, or Kodaira-Spencer theory of the curve. And it turns out this kind of parameterization of the deformation of the complex structure in terms of the chiral boson ends up reproducing these recursion relations, where this omega is a one-form reduction of the holomorphic three-form on the Calabi-Yau. Okay, so so far I have given a definition of topological strings. I've told you how you interpret it in terms of amplitudes of the M theory. I've told you how you compute them. I've told you some things about the large N dualities in this context. And now I would like to give applications in the context of black holes and gauge theories. So first I will start with gauge theory applications. So if you're interested in gauge theory application, let's say we're interested in 4D gauge theories with n equal to 2 supersymmetry. So suppose you're interested in, let's say, ADE gauge symmetry. We know how to engineer them. We take type 2A with an ADE singularity, and we fiber it over a curve. So we have a locus of ADE singularity along the curve. And this engineers for you, through this non-compact local description of the singularity, a four-dimensional theory. The modes living near the singularity leads to a four-dimensional gauge system of the desired type, and depending on what you intersect this singularity and so forth, you can engineer your gauge theory of your choice. And this was done a while back, and you can then ask, in this context, for these geometries, what does the topological string compute? The answer turns out to be extremely simple. The closed string topological amplitude for these kind of gauge systems, in the refined sense I talked about, are equal to the gauge theory partition function of Nekrasov. So the computation that one does in that context is identical to the partition function that one gets from this refined closed topological string. Now, there is also, you can ask, what about the open version of it? What does OpenThing do? Well, OpenThing does the surface operator version of Nekrasov, that you insert some surface operators in that story. That corresponds to putting these branes in the context of these toric geometries. And again, so we know what that corresponds to. This map, especially the second line, is not appreciated well enough, I believe, in our community, and it's not used enough. So some people working on this don't appreciate this connection, and this I think is important to understand better, because statements about the open string translate to statements about surface operators that we don't know yet. For example, the topological vertex formalism tells you that just from these trivial surface operators on a trivial theory with no bulk four-dimensional dynamics, so just involving surface operators themselves, one can get the partition functions of all gauge theories, period, of the kind that we get, of the kind that you have intersecting and so forth, just from those surface operators for all UN, not for a given UN. So it's not a surface operator in a given theory. It's a universal surface operator. So the statement that there's a universal surface operator in a theory with no gauge bulk gauge theory is the statement of topological vertex formalism. What does that mean from the 4D perspective is unclear, but it must have a meaning because we know that leads to the same computation that of Nekrasov partition functions. There are also 4D versions of these questions that one can ask. In this particular case, with n equals 4D versions with n equals to 1 supersymmetry by cutting the supersymmetry by half, basically by restricting attention to open kind of sector, where now we can fill the space-time with a D-brane. In other words, I said we have two options, either to take a two-dimensional subspace of R4 or fill the full R4 with the brane. So in this case, if we want to have a four-dimensional reduced theory, we just fill the whole space with these branes. And in this context, the geometric transition for the conifold can be interpreted as blue ball condensations in the context of the n equals to 1 gauge theory. And non-perturbative n equals to 1 F terms can be computed using the planar model of the corresponding matrix model. So the relation, since we know how to compute these diagrams in the context of internal theory, which involves matrix models, that leads to computation in this context of superpotential terms or F terms in these 4D n equals to 1 theories. So I'm being brief, so I'll move on quickly to the next set of things, which is basically the other set of application involving wall crossing. First of all, the meaning of wall crossing of BPS states in 4 dimensions and the connection with 4D BPS states. So the wall crossing phenomena has been observed and formulated in 4D with n equal to 2 and leads to a very beautiful formula of how if you know the BPS states in one region of parameters, and if you change, how do the BPS numbers jump? And there are various derivations of these formulas. And the one I want to talk about here involves the open A model. So it's an application of open topological string A model to try to derive these wall crossing formulas. And the idea is relatively straightforward. Well, not completely straightforward, but it's not too complicated either. You start with the n equal to 2 theory given by a Riemann surface. It's the Seiberg-Witten curve. And you have some BPS central charges, which I'm denoting here by a plane, where these vectors correspond to the periods of the Seiberg-Witten differential along the various cycles here. And what we want to do is instead of talking about the surface, I want to construct out of the surface, a two-dimensional surface, I want to construct the three-dimensional surface in the following way. We want to start from the n equal to 2 with 4D and break it to n equals to 1 in some sense, with considering a flow of this Seiberg-Witten curve, some flow that we call the R flow, where what happens is you take the central charges in the complex plane and you basically make them as a function of this extra parameter, this one parameter family, to run along straight lines in the central charge plane. So you get the three-dimensional geometry, which is a one parameter family, one real parameter family of Seiberg-Witten curves. And so you basically are enlarging the space in this form, and you can, it turns out, interpret this as a Lagrangian, and in fact better yet, special Lagrangian three-manifold. And you could then consider, for this particular case, the open topological string for this Lagrangian three-manifold that I told you about, and this becomes, of course, equal to Chern-Simon partition function on this Lagrangian manifold, as I told you already. Because of the map between open topological strings and Chern-Simon. Now, it turns out that in addition to this Chern-Simon topological string, Chern-Simon action, you get instanton effects each time the central charge of these central charge lines cross the real line. So these vectors are going from plus infinity to minus infinity. At some point, they cross the real axis. At that point, you get a correction or insertion of an instanton corresponding to the Wilson loop observable along the corresponding cycle of the Riemann surface. So topologically, you have a Chern-Simon theory, Riemann surface times R, and you get to insert these Wilson loop observables for each BPS state that you get, depending on the charge and also its spin. You get some formula like this. And it turns out that the invariance of the computation of the topological string in this context, namely compute these insertion of these operators, gives you the time ordered according to this order of the time, which order in which the particles flow and hit the real axis, gives you the wall-crossing formula. The fact that this formula is invariant under changes of the parameters of the underlying Sarbe-Witten curve gives you the wall-crossing formula. This also leads to an interesting statement, because if you consider M5 branes on such geometries, so from a given, so the statement is that if you start with a given 4D n equal to 2 theory, you can construct canonically a three-dimensional object out of it. And out of this three-dimensional object, you can consider the M5 brane on that three-dimensional object times R3. So you get automatically a three-dimensional gauge theory. So now it maps to a question in field theory. So out of a four-dimensional n equal to 2 theory, you're constructing an n equals to 2, namely half the supersymmetry, in 3 dimensions. And it turns out that the wall-crossing formula, the invariance of the wall-crossing formula, translates in this language to dualities of three-dimensional field theories. So dualities along the lines, for example, of the XYZ model with this U1 QED gets related to this wall-crossing formula for the Argyris-Douglas theory in particular. And there are also additional formula statements that are very surprising and still not deeply explained. If you compute the partition function of these M5 branes on such geometries for certain specific class of theories like Argyris-Douglas, you get the characters of conformal 2D conformal field theories out of the blue, which is not explained. And you get different characters depending on which line operator you insert. And the line operator algebra turns out to correspond to Verlind algebra, where the character Q here is related to the coupling constant of topological string, or if you wish, that twisted cigar that I mentioned before. Also, for the simplest class of models, one can have a geometry describe these Argyris-Douglas models, these Lagrangian geometries, in terms of the branch cover geometries over 3 manifolds. So you have a theory now which is characterized by some braids, and so somehow these braid theories, these nice braid geometries, characterize the 3D quantum field theory in this way. And so it's interesting to translate the maps, and it's possible to translate geometric aspects of these braids to statements about 3D quantum field theories. As other applications, we can talk about gauge theory partition functions. So if you take 4D or 5D n equal to 2 partition functions, so if you take 4D and the geometry S4 or their cousins, which is coming from 5-dimensional S4 cross S1, it turns out that the partition function that Peston studied in that context gets related, as we know, to the Nekrasov partition function squared integrated. And in this case, we know it's related to the refined one, depending on how you want to interpret it in topological string, with some specific choices of the refined parameter. And the question is why, in this language, why is this working like this? Where does this square come from? And one explanation would be is that if you think about the S4, you can break it into 2 pieces. And in this piece, basically half of S4 can be this geometry like S1 times half of S4, has a geometry exactly as a S1 times tab naught. And so the description a la the twisted tab naught, which gives you the left side to be the topological string, will be explanation of why you're on the left side getting the Nekrasov, and from the right side you get the other piece. Squaring is basically you're putting them together. So it's a simple explanation. Again, the detail of this perhaps can be better clarified, but basically that should be the rough idea. Also, the same thing leads to the 3D partition functions. And the story there is the same, namely you take the partition function of L times this S3 or S1 cross S2. And again, if you split the S3 or S1 cross S2 to 2 pieces, on this boundary you get this Melvin cigar. So the characters of these conformal theory look like square of these topological string answers. So in this case, the partition function of 2D conformal field theories, sum over the square blocks, end up being related to this fact that you're breaking into 2 halves. And so you naturally, out of these compact geometry, you get objects which look like modular invariant combinations of the characters of the 2D conformal field theory. Again, another bizarre fact. Now, in the few minutes I've got, I started a little late, I think, but I will hopefully try to finish on time. The BPS black hole count is also another set of applications. In this context, we can count 5D spinning black holes or 4D charged black holes. In the case of the 5D, what we mean is we consider the M theory compactified on Calabi-Yau threefold. We have a 5-dimensional space. And we consider M2 branes wrapped around 2 cycles of Calabi-Yau. These correspond to charged black holes. Or in the 4D case, we can take type 2A on a Calabi-Yau, and we can talk about D0, D2, D4, D6 brane bound states. Or in the context of type 2B, D3 brane. So in the context of 5D, it turns out the topological string partition function can be reformulated in terms of these degeneracies of the black hole. So if you count the number of black holes as n, with the charge d, where d is the charge of the black hole, and s is its spin, the sg2 spin, namely the 5-dimensional rotation group has a left and the right spin, then if you take the left spin part of it, this gives you a BPS black hole, spinning black hole, and this partition function is equivalent to the topological string. So the topological string is the partition function of the black hole, literally. So that's another way of formulating the A-model topological string. The refined version of this is also clear, namely the refined one, since it's non-compact, you can keep track of both the quantum SU2 left and SU2 right in the SO4 rotation group, and this leads to a refinement involving topological strings. And also you can do the 4D black hole story, basically by relating the asymptotic growths of the 4D black holes to properties of the topological strings. So this is probably familiar, so I'll be very brief. Basically, you introduce, you think about the parameters of the topological strings in terms of these parameters characterizing the moduli space of Calabi-Yau, these affine parameters of Calabi-Yau, which involves a Kähler parameter and extra one. And you reformulate the Kähler parameter divided by string coupling in this form, which characterizes H0 and H2 of the Calabi-Yau. You decompose the charge lattice of the type 2A in terms of the electric and the magnetic ones, H0, H2, and H4, H6. And you consider the charges, which I denote by electric and magnetic in this form. And you consider the mixed ensemble of the black holes if you denote n as the number of such charged state. And if you consider this mixed ensemble by summing over all the electric states with some chemical potential, it turns out that this is conjectured to be equal to the topological string squared with some choice of variable where x is given by the magnetic charge plus the, in the imaginary piece, having the chemical potential of this mixed ensemble. In fact, you can do something which looks tantalizingly related to something else. You can reformulate it and actually compute the number of black holes in 4D in terms of such integrals, basically by redoing the mixed ensemble and writing what the black hole means, and you get a formula like this. This formula means you take the topological string amplitude and its complex conjugate shifted with some integral of this form, and you're counting this. You can think of this another way. You can think about this as putting a black hole. What is a black hole? A black hole is a charged state with electric and magnetic charge. Or if you wish, that's equivalent to a line operator, because a black hole is a charged object, it's a particle. So it's like a line operator. So this is computation of the line operator in the context of this Calabi-Yau is getting related to this integral. On the other hand, this is reminiscent of the line operators one sees in the context of AGT, where you have these pieces, the left and the right piece squared, except shifted depending on precisely what loop observable we're inserting. And probably the reason is basically the same set of ideas I've already explained. We'll probably explain this, but again, it serves better to clarify this connection better. Now, there are questions having to do with open questions, which is basically the last topic I want to cover. There are many open questions, despite all the nice things we have learned. The main important question remaining, I think the main thing that I think I would love to know about topological string is what does it mean to talk about non-perturbative topological string? Almost everything I've talked about here involves perturbative expansions in some form or another. But the fact that there's this holomorphic anomaly, even though it sounded like a technicality, led to the statement that the topological string actually can be viewed as a wave function in a Hilbert space. And this is very interesting, and the interpretation of why this partition function is a wave function sounds a little mysterious. Perhaps one relation could be the fact that in the M-theory description I was giving you, there was a boundary to the space, and this thing lives on that boundary. So maybe that's one interpretation of why there's a wave function in the topological string. But maybe there's an internal version of this where this Calabi threefold can be enhanced with 7-dimensional space, and there's some speculation along these lines involving a G2 manifold where you contract some set of cycles of the Calabi to get some kind of a wave function. So, but anyhow, these are the kind of questions we don't understand clearly. In the Nekrasov-Shadashvili limit of the refined topological string, the topological string partition function leads to a wave function which is annihilated by the geometry, the open string wave function gets annihilated by the geometry of the corresponding curve, making this kind of connection even more tantalizing to understand. So the open string version of it is already in some sense understood in the Nekrasov-Shadashvili limit, but again, it will be better to understand even this in the context of the non-perturbative aspects of it, which is still remains to be understood better. Now also, does irrational moduli of Calabi make sense non-perturbatively? In the context of conifold, this would imply that the UN matrix model or UN Chern-Simon theory should make sense for irrational values of n. The fact that AGT makes sense for these values of n, if you map the corresponding AGT to the corresponding topological string question by this map between gauge theory and topological strings, it suggests that indeed it should make sense because the Liouville theory does make sense for irrational values of n. That can be done, and therefore this suggests that we should be able to make sense out of UN Chern-Simon or UN matrix model for irrational values of n. Also, this correspondence suggests that we should think about the topological string amplitudes as chiral blocks a la what we're familiar with in the context of 2D conformal field theories. And precisely what is the meaning of the structure of these conformal field theories for topological strings has to be better understood. Finally, how about n equals to 4 topological string? There's another topological string I haven't talked at all about, which involves the target space of Calabi twofold or hyperkähler geometries. How much of all of this structure can be carried over to there? Very little has been done in this direction. And it's also natural to actually broaden the story of topological string to what we could call topological branes, basically all the branes which preserve enough supersymmetry in all possible contexts in string theory is what I would think is what we should mean by topological strings. So topological branes would be just, by definition, supersymmetric branes which preserve perhaps a nilpotent supersymmetry. So understanding what is this class would be interesting. For examples involve, for instance, M fibers wrapping 6 cycles of a Calabi fourfold. How does this fit to this story and all that? So they should also be part of the story. And in fact, I would say that a large fraction of what we know about superstrings today involve these kinds of supersymmetry preserving amplitudes or questions. And so in this broad sense, the topological branes will involve more or less, in some sense by definition, most of what we know about superstrings today, and to try to understand what this subset means about the full superstrings. In some sense, topological branes would be the backbones of the full superstrings. So in conclusion, I would say that since its introduction in the more than 20 years ago, we have learned quite a bit about string theory. It's amazing that it reincarnates in different forms and it adapts to all the developments in different forms. It impacts new ideas and so forth. And it continues to surprise me all the time that each time I think that more or less we have understood what we need to do and we're almost done, a completely new direction opens up. And so I expect many more interesting physics to come out of this subject. Thank you.
Thank you for the beautiful talk. Are there questions or comments? We have not so much time, maybe 1 or 2 only. Yes.
That Q action on the top nut space as you go around the S1 circle, there are fixed points at the origin. Are there any physical implications of these fixed points?
There's no fixed points. The fixed points gives you the rise to the localization. That's precisely why you can actually compute them. It's similar to the kind of techniques that Nekrasov was doing in his instanton computations.
Thanks.
Ignatius?
It's just an idea. The 6-dimensional Calabi-Yau spaces, you could do a dimensional splitting and use Calabi-Yau spaces, more simple ones. A torus is also a Calabi-Yau space, but a fixed geometry. And then you could, this dimensional splitting would be that the 3 tori would be nested. Then you have come from 6 compact 6 dimensions to 3 times 2 dimensions, and they're all they're nested, and this nesting introduces an additional dimension. Then you would have topological structures, which is 3 times 2 dimensional plus 1 dimensional, that is in all 7 dimensional. And then it's much more topology even.
I'm not completely sure I understood exactly the question. If there could be a relation involving, for example, G2 manifolds that may be related to your comment, I'm not completely sure. In various contexts, it turns out that you can apply, of course, these circles of tiny size to get new statements about topological strings. For example, you can do the analog of the Fourier-Mukai transform on subspaces which involve T2s or T3 or whatnot, and get new statements out of what we already know about topological strings. For example, the partition function of n equals to 4 Yang-Mills on elliptic 4 manifolds can be computed using ideas from topological strings using these dualities.
Okay, we have just time for one question.
When you go to the non-perturbative definition of the topological string, it seems that the string coupling becomes an additional complex modulus. Now the question is why there is no holomorphic anomaly with respect to it, or it could be.
Well, the question is whether, these are very good questions which I don't have a deep answer, but I could just comment the following way. I'm not sure if non-perturbative topological string should make sense for complex coupling constant. For example, the embedding in M-theory suggests that it only should have a real, I mean, it is a phase. You cannot rotate Z1, and the tab knot does not have a complex multiplication as a symmetry. It's a rotational symmetry. On the other hand, you could connect it to a different picture that might suggest different y. So I don't think we have an answer yet to whether the coupling constant topologically should be viewed as a real parameter, non-perturbatively holomorphic parameter, complex parameter. Naively, it comes complex like the rest of the moduli, and they kind of might have some kind of a similar to the rest of the parameters, but in some sense also it's different.
Yeah, from the effective field theory point of view, I mean, the string coupling is the graviphoton self-dual, so that defines a complex parameter.
Yeah, the interpretation of the coupling constant is different. We know that it has to do with the spin. Also, the spin of the BPS states have to do with the coupling constant dependence, but it doesn't still necessarily mean that in the non-perturbative exact meaning it's a real or complex. We really want to understand what it means.